So we're on section 7.3. For the benefit of the people not watching these videos in order, there is no new mathematical or physics concepts on this chapter. We're just applying things that we've seen before. So all I'm doing here is showing you the examples, hopefully helping you see how to set out the questions and how to get the equations that we need. Now, in this one, we're dealing with friction and static particles. So if something is not moving, but there is friction involved, then what do we know? Well, we know if it's in limiting equilibrium, then friction is equal to mu times r. And if it's not in limiting equilibrium, then friction is just as big as it needs to be to make the forces balance. Now, if that doesn't make sense to you, then go back to chapter 5, I think it was, where we discussed friction, and there are videos on this playlist for that channel as well, for that chapter as well. So let's go straight into the examples. As before, I can't give you comprehensive examples of every possible situation they can give you, but if we go through the examples in the textbook, that should be enough information to get you into the habits that we need. So we've got a mass of 8 kilograms resting on a rough horizontal plane. So rough horizontal plane tells us there is friction. The mass is 8 kilograms, tells us there's an 8g force acting downwards. The mass may be modelled as a particle, and the coefficient of friction between the mass and the plane is 0.5. So we like to write down our coefficients of friction near the diagram to remind us. Find the magnitude of the maximum force P, which acts on this mass without causing it to move. First of all, if P is horizontal. Well, we got this pulling downwards, we got R pulling upwards, we've got a friction force, we've got a force pushing or pulling, and then the friction force is going to act in the opposite direction. So, if this is acting horizontally, what's the maximum it can get to? Well, the maximum it can get to is the bit where the friction is equal to mu times R. If that pulling force makes this friction equal mu R, then it's as big as it can be. Okay, that's any bigger, and the object will start moving. That's what we mean by limiting equilibrium. That's what we mean by F max equals mu R. So it doesn't matter what the diagram looks like. We're going to apply, as before, our two ideas. We're going to go vertically. The forces balance out, so resolving forces vertically, upwards forces equals downwards forces. Resolving horizontally, rightwards forces equals leftwards forces. Let's look at these two equations. We've got R is 8g, we can substitute that into here, and we get P equals mu is 0.5. Okay, so same thing as before, we wrote down those two equations without worrying about how difficult they were going to be to deal with. In this case, they're easy to deal with. In other questions, they're not going to be quite so easy to deal with, but that is the calculation that we're going to type in our calculator. And just looking at this, it comes up to 39, okay? 39 to two significant figures, at least. Now, the next one says, well, what if we want to pull this along, but imagine we've got this as a heavy box on the floor or something like that. We've got 8g downwards, we've got the reaction upwards, but this time we're going to attach a rope to it and pull it, but we're not going to crouch down to the floor and pull it horizontally. We're going to pull it at an angle of 60 degrees. And we've got a pulling force there. We want the maximum possible pulling force, so that means it's on the point of slipping, so that means the friction force is mu r, and mu is again 0.5. We've only got, it seems like we've only got one idea for so far in this chapter. We've got about 3 or 4 ideas, but feels like one at the moment. Forces upwards equals forces downwards. R plus P sine 60. So there's my R force. Here's my P force. Part of that P force is acting upwards. Which part of it? Well, P is the hypotenuse. There's the angle. The bit that we want is opposite, so P sine 60. If you're not comfortable with that, then go back in the playlist and revise that particular idea of going straight to P sine 60. 8g is pulling downwards. Right and left, we get P cos 60 degrees equals mu r. There's equation 1. There's equation 2. We need to find P. We can find P and R. Well, and remember, we know mu is 0.5. So look at these two equations. The only things that we don't know are P and R. They're two simultaneous equations, so we should be able to solve them. Probably the way to do it here would be to take equation 2 and substitute into equation 1. So I'd rewrite equation 1 as P cos 60, substitute 2 into 1. Really important to write this sort of thing down. So even in an example, I don't like doing anything without saying what we're substituting into where. So instead of r, I write p cos 60 plus p sine 60 equals hg. Sorry, instead of p cos 60 divided by 0.5, I should say, shouldn't I? So r equals p cos 60 over 0.5. Substitute that into there. And that's how we're going to find p from this one. So write down the equations and work from there. That method is still working for us. Next thing we've got a box, mass 10 kilograms, resting in equilibrium on a rough plane at 20 degrees to the horizontal. So here's my plane. This angle here is 20 degrees. Here is the object that's sitting on it. That's got a weight acting downwards, which in this case is 10 times gravity because the mass is 10. It's got a reaction force pushing out from the plane. Put this dotted line in here, 20 degrees on there. Okay. It's in limiting equilibrium on a rough horizontal plane inclined at 20 degrees above the horizontal. So there is friction, and it doesn't tell us there's any other forces at the moment. So this is trying to slide down the plane. Friction is moving it up the plane. And in this case, the friction is equal to mu times r because the equilibrium, it says, is limiting. And that's all we have. So we'll have to work with that. Let's go in this direction first, parallel to the plane. It is in limiting equilibrium, but it is in equilibrium. So the forces up the plane equal the forces down the plane. Up the plane, I've got mu times r. Down the plane, I've got 10g sine 20 is the component of this 10g force, which is opposite the 20 degree angle. So 10g sine 20 degrees, and that's equation number 1. There's only 3 forces. Those two act up and down the plane a bit, and r is perpendicular to the plane, so it doesn't. Perpendicular to the plane, there is no acceleration, so the forces balance out. Forces out from the plane are r. This one doesn't act in or out. This one does push down into the plane. How much of it pushes down into the plane? Well, 10g cos of 20 degrees, because it's the bit that's adjacent to the angle. So 10g cos 20 degrees. There's equation 2. We've written our equations down, and now we should have everything we need. We've got 2 simultaneous equations. There are 2 unknowns, a mu and an r. In this case, I can substitute straight from equation 2 into equation 1, and I get mu times 10g cos 20 degrees equals 10g sine 20 degrees. But normally, you know, I've done that next stage because it's staring us in the face there. But the important thing is from here, we've got 2 simultaneous equations with 2 unknowns in. We know all of these numbers, we know all of these numbers. So all we've got to do is work from there. Bit of work for a calculator, and there's mu, okay? Part B of this example. A horizontal force of magnitude P is applied to the box. Given that the box remains in equilibrium, find the maximum possible value of P. Now, if we've got this situation and it's in limiting equilibrium, have you noticed the question doesn't tell us whether P is going to be horizontal this way or horizontal that way? Well, if I started pulling this way, if I started pulling in this direction, can you see that if this is already in limiting equilibrium, all we need is the tiniest amount of extra force down the plane and it's going to start sliding. So I can't apply a force down the plane and expect this thing to stay in equilibrium. So therefore, we need to apply a force up the plane, okay? I say there's no new maths in this chapter, but we do have to use our sort of all the information that we have in clever ways sometimes. So that's how we know the force is pushing in that direction. So once we know that, what do we have? We've got a weight acting downwards, a reaction going that way. We've got mu times r, mu r going down because it says we want the maximum possible value of P for it to stay in equilibrium, so we know the equilibrium is going to be limiting. I've got this force pushing. I like to start my forces on the object and drill them from there. I know that this angle here is 20 degrees still. This angle here is 20 degrees. By the way, if you notice that I don't bother trying to make my angles anything like the angle that they're you know, I've not paid attention to the 20 degrees and drawn it any different to an angle if they said it was 40 degrees. That's partly laziness, but it's also partly that I know I need enough space here and here to write the numbers in on my diagram. So you might find it better to try and adjust the size of your angle, depending on what angle they tell you it is. I find it better to say, well, I'll make my diagram look a bit inaccurate, but I'll have room to put all the numbers on it. Up to you. Whatever makes it clearest to you. So I've got p newtons pushing that way, r that way, 10 that way, and mu r that way. And those are all my numbers. Now I know from part A that the coefficient of friction is, well, it ended up as, we didn't work it out, but the book tells us 0.36. And I can use that now because this is the same object and the same plane. So the coefficient of friction between the two is going to be the same. So we've still got 0.36. Now what can we do? It's in equilibrium. Can you see, I mean, if you are watching these videos in sequence, can you see how many times we just do the same things? It really is coming down to the same few techniques. Even when this chapter gets a bit, I mean, you might think it's nasty enough already. It gets a bit nastier, but we still do the same sort of techniques. Resolving, I'm going to go perpendicular to the plane first this time. Out from the plane, we've got R. This one is parallel, so it doesn't act out or in. This one gives us an inwards into the plane component of 10g cos 20 degrees. This one here gives me an into the plane component, if I split it up like this, of p sine 20 degrees. And there's equation number 1. I'm going to go for resolving forces parallel to the plane this time. This one pushes out for the plane, so it doesn't count. Down the plane, we've got 0.36 r. I've got the down the plane component of this force, which is 10g sine 20, and I've got the up the plane component of this p force, which is p cos 20 degrees. That's equation number 2. There are my two equations. Now, if they don't solve this for me, then I'm pretty stuck because I've used all the information that I've got. But if we look at it, we need the value of p, and the equation here. What are the unknowns? I've got an r and a p that I don't know. Here I've got an r and a p that I don't know. So I could take that lot and substitute it into there where that r is, and then I've got an equation with only a p in that I don't know. Okay, the numbers in there are a bit nasty. There's sines and coses of 20, and there's a g which is 9.8, and all sorts of nasty things, but you know what, we've got a calculator, so it can't be that bad, can it? Okay, those are all the examples on 7.3. Good luck.